What I want to look at here is something called the Lorentz force law, but before we get to the Lorentz force law, let's remind ourselves that when we had a wire, we had a magnetic field that went round in a circle. We sort of defined ends with this bar magnets and stuff like that, and we would say, hey, that's a north, that's a south in these field lines, but we said they go all the way, they go around in loops. So there is no real end to a magnetic field line. It just goes in a circular motion. It can go one way or the other, and they can cancel out. That was something else we learned. What if the magnetic field lines are going into the paper? Then we draw them like this. That means the magnetic field lines are going into the paper. Now, if they're coming out of the paper, then we just draw them as dots, like this. All right, and we're going to be using our right hand slap rule. Now we use the right hand grip rule for the wire. We use the right hand solenoid rule. Now we've got what's called a right hand slap rule. We're going to be using that a lot, and I'll describe it a bit more when I do the Lorentz force law. But with these charges going into the paper, when you're using your right hand, your fingers, as opposed to your thumb, your fingers always point in the direction of the field. So into the paper, boom, out of the paper for the dots, this way. All right. Now, let's see if we can apply this to something called the Lorentz force law. The right hand rule, you'll hear some other rules. When I was at school, my physics teacher taught me a left rule and a right rule, and it all got confusing, but we just use the right hand for everything. And it's quite easy. And the right hand slap rule, the fingers will always give you the direction of the magnetic field. The thumb will always tell you the other thing that you know, and the slap will tell you what you're looking for. So let's have a look at something called the Lorentz force law. Now, the Lorentz force law is the force on a moving charge. Now remember, with electricity we had F equals EQ, E being the electric field. That was the electrical force in an electrical field on a stationary charge. When a charge is moving and it's in a magnetic field, it feels a magnetic force. Now you only get a magnetic field if another charge has moving in the first place to create that field, and then another charge comes along and it's moving, then it will experience a force. Whereas if the other charge in that magnetic field is not moving, it does not feel the magnetic force. So force on a moving charge, Lorentz force law. To me, most important law, and a lot of physics teachers do not focus on it enough, and yet it really is the fundamental thing that goes on, is that you've got a magnetic field. If a charge is moving in it, it will experience a force. Very fundamental. Now, we'll just give you the equation straight off, BQV. Now, B is the magnetic field in Teslas, Q is the charge, force as usual is in newtons, but the V is for velocity, not for voltage. All right, velocity. So let's draw a field into the page. Now I could give this a strength. I could say B equals 1.2 Tesla, and so I've given it a strength. Now I can then get that out of the way. I can then bring me a little charge coming along, and I'll call it a plus charge, and we'll give it a strength of 10 nanocoulombs. Alright, so what are we missing? We've got B, we've got Q. It's got to have velocity. No velocity, no magnetic force. So let's give it a speed of, I don't know, 1,000 meters per second. Pretty fast. Alright, so the force is just BQV, which equals 1.2. That's actually quite strong, by the way. Times the charge, 10 nanocoulombs. How do we convert nanocoulombs? Nanocoulombs are billionths of a coulomb. So a billionth is just divided by a billion, which is times 10 to the minus 9. So 10 nanocoulombs. And times the velocity, 1,000. So we can soon do that. we do it on our little calculator here, and we go 1.2 times 10 exponent minus 9 times 1000, and we get an answer of 1.2 times 10 to the minus 5 newtons, because this is a force. So that's the Lorentz force law. But we're missing something here, and what we're missing is direction. And this is where we use the right hand slap rule. And what you do is your fingers point in the direction of the field, your thumb gives you the direction of the velocity, and your slap up gives you the direction of the force. So this little charge, as it comes through here, is going to experience a force up. That's its velocity, that's its force. Now, the right hand slap rule is for positive charge. Positive charge. So, if that had been an electron, it would be in the opposite direction and down. So, what's going to happen if there's always a force at right angles to the velocity? So we're going to get a circle. It's going to go in a circle. This is how they make charged particles go in circles with the big colliders. So that's all pretty cool and reasonably easy. Now, if we look at this other aspect, when I had my field going into the paper and my velocity was going like that, that velocity is at right angles to that field. Field in, velocity across. That's right angles. If the velocity had been straight in line with the field, then there's no force. Okay? There's no force. So the component of velocity in the direction of the field has no force, or there is no force on it. So if your total velocity is in the direction of the field, there is no force. So with vectors, you can always work out components, even in 3 dimensions. And you can go, what component? So you only use the component that is perpendicular to the field. Only use the perpendicular component. Alright? And that's the Lorentz force law.